On the 1st of July, 2025, at precisely 14 hours and 37 minutes Universal Time, the night sky over Chile's Atlas survey station shattered our cosmic complacency. A faint smudge appeared on the automated telescope's sensors, a dot streaking through the starfield at 4.5 astronomical units from our Sunday. Within hours, the calculations poured in like a sudden storm, revealing a visitor unbound by our solar system's rules. A hyperbolic path with eccentricity soaring beyond 1, meaning it would blaze through once and vanish forever into the galactic abyss. Designated C/2025 N1 Atlas, but whispered among astronomers as 3I Atlas. This third confirmed interstellar wanderer arrived not with quiet grace, but screaming at 130,000 miles per hour, or 209,000 kilometers per hour. That's not mere speed. It's the fury of another star system's momentum, multiplying a bullet's velocity by 170 times, carrying secrets that evaporate our certainties like ice under sunlight. As Zen, your guide through the whispers of the cosmos on Cosmic Mysteries for Sleep, I invite you to lean back, let your eyelids grow heavy, and drift with me into this enigma. 3I Atlas isn't just a chunk of rock and ice the size of a small city. It's a paradox, breathing vapor into the void. Telescopes like Gemini North in Hawaii turned their 8-meter mirrors toward it days after discovery, unveiling a fuzzy coma, a cloud of dust and gas erupting as our sun's warmth awakened ices dormant for millions of years in the interstellar cold. This wasn't a dead relic. It was alive, sublimating directly from solid to gas, forming an ethereal shroud in space's vacuum. The implications hit like a meteor, an object battered by radiation that would erase life on Earth, chilled to degrees above absolute zero, yet stirring at the sun's gentle touch. And the path? A surgical thread through planetary orbits. Closest to Earth, at one point, 8 astronomical units, 270 million kilometers safe, yet perfectly positioned for our gaze, as if the universe had scripted this reveal. But the mysteries deepened with every glance. The James Webb Space Telescope, our infrared sentinel in orbit, captured spectral signatures on the 6th of August, 2025, shattering expectations. Carbon dioxide dominated, outpacing water in an 8-to-1 ratio, a reversal of what we see in our solar system's comets, where water reigns by factors of 10 or more. Even the driest local comets rarely tip beyond 2-to-1. Here was 3I Atlas, flaunting extremes that placed it alone in the cosmos. Then, between the 8th and 12th of August, NASA's SphereX mission mapped an emission cloud, stretching 348,000 kilometers, 250,000 miles, engulfing distances vaster than Earth's lunar orbit. Imagine that scale, a nucleus mere kilometers wide, sustaining a gaseous sphere large enough to swallow planetary paths. This wasn't simple sublimation. It hinted at processes on scales defying our physics. Perhaps fragmentation of carbon dioxide-rich chunks, or solar wind amplifying a hidden gas reservoir. Drawing from real interstellar guests like ʻOumuamua in 2017, that cigar-shaped tumbler accelerating without visible outgassing, sparking debates from hydrogen vents to speculative sails, and 2I Borisov in 2019, with its carbon monoxide excess suggesting birth in a frigid outer disk. 3I Atlas paints a galaxy of diversity. Oumuamua's subtle push, 100,000th of Earth's gravity, remains unexplained, a whisper of forces beyond our grasp. Borisov's textbook tail and water vapor felt familiar, yet its chemistry screamed of alien nurseries colder than our Kuiper belt. Now, 3I Atlas, with its carbon dioxide cloak, suggests formation near a warmer snowline, where water vaporized, but carbon dioxide froze a zone like our asteroid belt, but in a distant star's embrace. These visitors aren't anomalies. They're samples from a vast debris field, each carrying isotopic fingerprints of stellar births billions of years ago, when the universe was half its age. As we unravel this, picture the global chase. NASA's Hubble constraining the nucleus to under 3.5 miles across, yet brighter than size suggests, hinting at reflective ices, or something stranger. Gemini South in Chile confirmed the antisolar tail in late August, a gossamer thread barely visible, as if playing hide-and-seek with our theories. Swift Observatory spotted hydroxyl radicals, signs of water breaking apart, but SphereX found the signal faint, upper limits contradicting expectations. Is water trapped beneath an insulating crust, forged by interstellar radiation? Or does 3I Atlas hail from a water-poor cradle, its chemistry a testament to galactic variety? These questions don't overwhelm. They invite wonder, a gentle unraveling in the quiet of night. And speaking of quiet moments, if this cosmic tale is easing you toward rest, why not share your own starry postcard? Like this episode if it sparks your curiosity. Subscribe to Cosmic Mysteries for Sleep so we can journey together more often, and drop a comment below with where you're listening from and what time it is, perhaps under a midnight sky in New York or dawn in Tokyo. Your words connect us like constellations, weaving our shared awe into the night. Returning to our wanderer, the dynamics add layers of intrigue. Unlike ʻOumuamua's mysterious acceleration, 3I Atlas follows gravitational predictions so far, but its extended coma challenges models. How does a small core sustain such vast emissions? Perhaps ionized carbon dioxide interacts with solar magnetic fields, accelerating gas to create this ghostly envelope. Or it's a loose aggregate, fragments outgassing independently, a flying gravel pile defying our comet blueprints. Hubble's photometry shows stable brightness, no periodic variations betraying spin, suggesting slow rotation or uniform surfaces. Each possibility a clue to origins in the Milky Way's thick disk, among stars 8 to 12 billion years old, when cosmic noon peaked in star formation. Speculation blooms here, blending fact with the thrill of the unknown. Avi Loeb, that Harvard provocateur, posits technological angles. Could self-luminosity from internal sources explain the activity, or optimal geometry hint at guided paths? But grounded explanations hold sway: radiation, processing, altering chemistry during eons adrift, or temperature dependencies favoring carbon dioxide at current distances. As perihelion nears, post-conjunction spectra in December might show water surging if heat cracks the veil. Testing these ideas in real time, this visitor isn't just data. It's a mirror to our place in the expanse. Before 2025, we had ʻOumuamua and Borisov. Clear models, instruments ready. 3I Atlas evaporates that hubris. Its carbon dioxide dominance, a reminder that the galaxy harbors recipes we can't fathom, perhaps from low-mass stars with extended icy disks, or luminous ones, favoring carbon volatiles. The irony, a messenger from light years away, lingering just long enough for study, yet fleeting, demanding we seize the window before it slips back to the stars. In this dance, humanity's finest tools, Hubble's artful streaks, Webb's molecular maps admit defeat against a city-sized enigma. Yet defeat breeds discovery. Proposals for Comet interceptor in 2029, waiting at Lagrange points for the next arrival. Rubin Observatory's sky maps uncovering dozens yearly. 3i Atlas awakens not fear, but readiness, a soft call to explore the unknown with open hearts. As your breath slows, let this tale cradle you, the universe's secrets, unfolding like petals in dawn's light, each revelation a step toward deeper peace. Picture the solar system as a grand celestial clockwork, where planetary orbits tick with predictable precision, and now envision a rogue element, a bullet from beyond our galaxy, streaking through this machinery with impossible grace. 3i Atlas embodies that intrusion. Its path, a masterpiece of cosmic timing that feels almost orchestrated, as if the stars themselves conspired to grant us this fleeting spectacle. Threading between the gears of our neighborhood, it approaches perihelion on the 29th of October, 2025, not at the distant fringes like most comets, but scorching between Earth and Mars, 130 million miles from our Sunday. Close enough to boil ancient ices into vapor, yet distant enough to survive intact. This journey reads like a scripted tour, written eons ago in the language of gravity and momentum. The geometry unfolds with theatrical flair. As 3i Atlas hurtles inward, Earth positions itself on the sun's opposite side, cloaking the visitor in glare for nearly 2 months from late September through early November. It's a cruel twist, hiding the peak activity when solar heat drives the most dramatic outgassing, the nucleus shedding material in bursts that could reveal its deepest secrets. Yet this blackout sparks ingenuity among astronomers, turning frustration into opportunity. On the 3rd of October, 2025, the comet streaks past Mars at just 29 million kilometers, closer than the red planet's own moons. Robotic explorers like the Mars Reconnaissance Orbiter, with its high-resolution camera, stand ready to capture images from this alien vantage, peering through the dust and gas while Earth remains blind. These snapshots might unveil asymmetries in the coma, directional jets invisible from our perspective, or even subtle fractures hinting at internal stress from the sun's pull. Drawing from historical precedents, recall how early astronomers like Galileo Galilei gazed at comets through rudimentary lenses, interpreting them as omens or atmospheric phenomena, unaware of their extraterrestrial origins. Today, we build on that legacy. With instruments that Galileo could scarcely dream of, yet 3i Atlas echoes those ancient wonders, its trajectory evoking the great comets of old that inspired fear and awe. Unlike Hale, Bop's brilliant tail stretching across 1997's skies, or Neowise's 2020 glow, this interstellar guest keeps a subtler profile. No naked eye blaze, just a faint, fuzzy star at magnitude 11 or 12, demanding telescopes to witness its passage. But that restraint heightens the intrigue, inviting us to ponder what lies beneath the modest veil, perhaps ices forged in a star system's nursery where conditions birthed chemistries alien to our own. The orbital mechanics whisper deeper enigmas. 3i Atlas moves not just fast, but wrong. Its hyperbolic curve suggests an origin velocity of 25 kilometers per second relative to our galactic rest frame, fast enough to escape not only our sun's grasp, but perhaps the local stellar cluster's embrace. This isn't fresh ejecta from a nearby berth. It's an ancient nomad, wandering the Milky Way for epochs, surviving supernovae blasts and gravitational tugs that reshaped its path countless times. Tracing backward, calculations point to the galaxy's thick disk, a realm of older stars formed 8 to 12 billion years ago during cosmic noon, when star birth peaked and heavy elements enriched the void. If born there, 3i Atlas carries frozen echoes of that era, a time capsule from when the universe was half its current age. Its composition, a snapshot of planetary formation in metal-poor environments where carbon volatiles dominated over oxygen-rich ones. Come spring 2026, the comet graces Jupiter in March, a distant rendezvous sparking proposals to redirect NASA's Juno spacecraft from its gas giant studies toward an intercept. Juno, probing Jupiter's depths since 2016, could pivot with precise burns, leveraging the planet's gravity as a slingshot to chase this fleeting prize. It's audacious, transforming a mission built for atmospheric secrets into humanity's first close brush with interstellar matter. But the geometry aligns, offering a chance to photograph the nucleus up close, measure its magnetic interactions, or sample ejected particles that encode alien histories. Success would rewrite exploration paradigms, proving we can adapt on the fly to cosmic surprises, much like how Voyager probes in the 1970s pivoted to grand tours after initial Jupiter aims. Yet the path's precision raises quiet questions, blending fact with fancy. Why this needle thread through orbits, aligning for optimal viewing from multiple worlds? Real data from predecessors like Borisov showed similar serendipity discovered approaching the outer system, allowing months of prep while ʻOumuamua escaped detection until outbound. 3I Atlas hits the sweet spot. Spotted far enough for planning, close enough for detail. Is it chance? Or does the universe favor observers? Hypotheses swirl. Perhaps statistical flukes in a debris-filled galaxy, or subtler forces guiding ejections from distant disks. Grounded in science, we know hyperbolic orbits demand ejection velocities from giant planet slingshots or stellar flybys. Processes common in chaotic young systems, yet the alignment feels bespoke, stirring that ancient human urge to see patterns in the stars. As the comet climbs toward Leo in December's pre-dawn skies, racing outward at over 150,000 miles per hour, it grows fainter, a final act before the galactic curtain falls. Amateur scopes might catch its glow, a fuzzy point among millions, no tail like Hyakutake's 1996 arc, but profound in subtlety. This window, 3 months pre-conjunction, 6 weeks post, demands urgency, a race against dimming light and increasing distance. Telescopes Marshall, transiting exoplanet survey satellite hints at early activity beyond Jupiter's orbit, implying volatiles more sensitive than water, perhaps supervolatiles awakened by faint solar whispers. Blending these realities with the unknown, consider how 3I Atlas might harbor organics preserved in its ices, molecules that could mirror those seeding life on early Earth. Panspermia theories, rooted in observations of comets delivering water and amino acids, gain traction here. An interstellar courier potentially carrying building blocks from another world's failed biosphere. Not proven, but the chemistry teases. Carbon dioxide dominance might indicate intermediate zones where complex organics formed without water's interference. A hypothesis testable, as the comet warms and vents trace compounds for our spectrometers to sniff. The choreography extends to future passages, with Rubin Observatory's 2025 debut promising 1 to 70 interstellar finds yearly, transforming rarities into routine. Comet Interceptor, launching 2029, waits poised at stable orbits, ready to redirect toward the next arrival. Armed for high-speed flybys that capture dust and spectra mid-flight, 3I Atlas paves this road. Its quirks, subtle tail, elongated coma, guiding designs for instruments that pierce such veils. In this vast timeline, our brief intersection humbles yet empowers. A reminder that while the comet spends less than 2 years in our vicinity, the knowledge gleaned echoes eternally. As you settle deeper into relaxation, following its arc through mental skies, the journey invites reflection on our own paths, transient, yet capable of profound impact. I'm curious, where are you listening from tonight? And what time is it there? When the Hubble Space Telescope locked onto 3I Atlas on the 21st of July, 2025, The universe handed us a vision that blended the familiar with the utterly foreign, a soft glow against endless black that reshaped our expectations in an instant. The image revealed a teardrop-shaped cocoon of dust and gas elongated away from the sun's direction, as if sculpted by invisible hands of radiation and gravity. At its core, the nucleus remained a stubborn point of light, unresolved even by Hubble's sharp optics, allowing scientists to cap its size at no more than 3.5 miles across or 5.6 kilometers a scale, smaller than many earthly cities, yet commanding a coma that sprawled thousands of miles in every direction. This wasn't the cold, inert rock we'd anticipated from interstellar depths. It was a dynamic entity, its surface awakening under solar warmth, transforming thermodynamics into a spectacle that turned scientific documentation into unintended poetry. Tracking the comet against fixed stars, Hubble kept 3I Atlas centered, causing the background to streak like luminous trails, evoking a sense of motion that separated this wanderer from our solar family's steady rhythms. The coma itself narrated a tale of revival, crossing the 4 astronomical unit mark, where water ice begins to sublimate vigorously. The nucleus liberated dust particles from their icy bonds, forming a spherical cloud with that distinct sunward elongation. Solar radiation pressure pushed finer grains outward, while gravity tugged the whole structure into its characteristic shape. Yet the anti-solar tail, expected to fan prominently away from the sun, appeared puzzlingly faint, almost elusive in early views, a subtlety that hinted at viewing angles compressing the feature or dust grains too large to yield easily to photonic winds. By late August, Gemini South's deep imaging in Chile finally unveiled it, a delicate thread confirmed in astronomers' telegram number 17,363, affirming theory while underscoring how this visitor bent visibility rules to its own whims. Dust loss rates matched solar system comets at similar distances, a comforting parallel at first glance, yet jarring given the object's interstellar odyssey. Exposed to cosmic rays that should have stripped volatiles and altered surface bonds, 3I Atlas behaved like a pristine comet on its maiden solar plunge, its activity defying the erosion of epochs. Hubble's resolution, among the finest from orbit, mapped coma morphology, but failed to pierce the nucleus veil, leaving rotation and surface features as enigma's point sources buried in self-made fog, like examining a distant flame through its own haze. Subtle brightness gradients suggested active vents, specific regions erupting material in patterns that whispered of uneven composition, perhaps pockets of volatiles clustered from its birth disk. Photometry added intrigue, brighter than size constraints implied, suggesting either a reflective surface gleaming with fresh ices or a nucleus larger than upper limits allowed. Dark, carbon-rich exteriors would dim the glow. Bright facets could explain the luminosity, opening doors to speculations about formation in zones where ices condensed pure and unweathered. As August waned into September, Hubble chronicled the coma's growth, solar heating intensifying the expansion. Yet the core stayed veiled, a cosmic coyness that built anticipation for complementary views from other eyes in the sky. Shifting to the infrared realm, the James Webb Space Telescope's analysis on the 6th of August unveiled the chemical shock that redefined 3I Atlas. Spectral lines blazed with carbon dioxide dominance, an 8-to-1 ratio over water that flipped our cometary script. Local comets favor water by orders of magnitude, even the parched ones, rarely exceeding 2-to-1. This extremity carved a niche of 1, prompting whispers of environments where carbon dioxide snowlines dominated, perhaps in disks around stars where temperatures allowed liquid water but froze carbon volatiles. Webb's precision mapped emission lines. Water's signal muted to near silence, questioning if significant hydration existed at all, or if photodissociation hid it in hydroxyl fragments detected earlier by Swift. SphereX's wide-field mapping between the 8th and 12th of August amplified the anomaly. Carbon dioxide emissions sprawled outward for at least 348,000 kilometers, a colossal envelope dwarfing planetary orbits, large enough to encompass the Earth-Moon system, and then some. Such scale demanded rethinking cometary physics. How could a kilometers-wide heart sustain this? Fragmentation theories emerged. Perhaps carbon dioxide-rich shards broke free, sublimating across vast volumes, or solar wind ionized the gas, electromagnetic forces stretching it beyond thermal expansion's reach. These mechanisms stretched boundaries, echoing real puzzles from Borisov's carbon monoxide excess, born in colder realms, versus ʻOumuamua's dry silence, perhaps devolatilized by relentless radiation. Absorption features at 1.5 and 2.1 micrometers hinted at water ice in solid form, locked in surface layers yet reluctant to vaporize, as if an organic mantle insulated it, selectively permitting carbon dioxide's escape. This selective volatility painted a portrait of layered evolution, interstellar journeys forging crusts that suppressed water while favoring more volatile cousins. Contrasting with Borisov's water vapor tail and Oumuamua's lack of detectable gas, 3I Atlas suggested a middle ground formed in intermediate temperatures, analogous to our asteroid belt, where water vaporized but carbon dioxide condensed, a chemical sweet spot yielding this water-poor, carbon-rich enigma. The implications rippled outward, challenging planetary formation models. If typical of interstellar debris, our theories miss key pieces: the trio's diversity, Oumuamua's acceleration enigma, Borisov's cold disk signature. 3I Atlas's warm zone vibe hints at a galaxy teeming with varied ejecta, each a core sample from alien worlds. As September loomed, narrowing the pre-conjunction window, data painted an unprecedented yet incomplete picture. Extraordinary chemistry demanding explanation, whether new object class or extreme physics at play. Delving deeper, consider the organic potential woven into this chemistry. Carbon dioxide dominance might cradle complex molecules, shielded from radiation in the nucleus depths, emerging as the sun warms layers. Real comets, like Halley's 1986 flyby, revealed organics, amino acids, hydrocarbons that could seed life. Panspermia, bridging stars. 3I Atlas, from an ancient thick disk, might carry primordial recipes from cosmic noon's frenzy, when heavy elements first enriched disks, fostering chemistries ripe for prebiotic sparks. Not a certainty, but a tantalizing thread, urging us to scan for sulfur species, noble gases, traces that encode radiation history and parent system's metallicity. Hubble's August evolution captures showed the coma ballooning, dust distribution uneven, brightness stable yet suggestive of localized jets, active sites venting in rhythms tied to rotation or solar angle. Without multi-angle views, these patterns lingered as hieroglyphs, decoding delayed until post-perihelion emergence. The irony deepened. Instruments worth billions, minds honed over generations, all focused on a transient that withholds as much as it reveals. A humbling echo of how the cosmos guards its depths. SphereX's water ice detections contrasted Swift's hydroxyl, a drama unfolding in data. Streams water present but trapped, or observational artifacts veiling truth. Tail morphology added puzzles, anti-solar subtlety, implying large grains resistant to pressure, or geometry flattening the plume. Each clue layered curiosity, building toward perihelion's unseen climax, where heat might shatter barriers. unleashing signatures that resolve or confound. In this unfolding narrative, 3I Atlas transcends observation, becoming a lens on galactic diversity, its chemistry, a bridge to unseen systems, where stars of varying masses sculpt disks with unique thermal gradients. Low luminosity stars might extend carbon dioxide zones, yielding such volatile-rich wanderers. Brighter ones could drive reactions favoring this imbalance. Radiation's role looms large, high-energy particles rearranging bonds over millennia, preferentially preserving carbon dioxide while dismantling water, a hypothesis testable through reddish spectral hints of processing. As the comet's activity hints at structure within brightness, variations mapping vents like volcanic hotspots on a miniature world, the stage sets for December's reappearance, when Virgo's pre-dawn hosts its fading glow, climbing to Leo as distance claims it. This chemical surprise, timed as viewing wanes, underscores the urgency. A laboratory powered by our sun, carrying alien history, yet destined to reclaim its mysteries unless we grasp them now. The progression from Hubble's visual baseline to Webb's molecular revelations marks a symphony of discovery, each instrument harmonizing to peel layers from this enigma. Yet for all the data, the visitor remains a tease, its heart veiled, chemistry extreme, origins ancient, a wanderer that demands we question not just its nature, but our place in a universe where such gifts arrive unbidden, stirring the soul with possibilities that stretch beyond the stars. Blending these threads, the coma's teardrop form and chemical extremes evoke a living entity, breathing in solar energy and exhaling vast clouds, a process that might mirror primordial atmospheres on distant exoplanets. Real exoplanet studies via Webb show carbon dioxide in hot Jupiter's skies, but 3I Atlas offers a frozen sample, perhaps from a system's formative disk, where such gases condensed into planetesimals that never coalesced into worlds, instead flung into the void by gravitational chaos. This interplay of fact and wonder fuels the chase. As astronomers' telegram updates ripple through networks, each datum a step toward understanding or deeper mystery. The carbon envelope scale, defying nucleus size, suggests distributed sources fragments trailing like a comet's retinue, each sublimating in concert or amplified by plasma interactions, solar wind sculpting the gas into magnetic structures unseen in local comets. As we ponder, the narrative builds to more. What if trace organics emerge post-perihelion, isotopic ratios matching early galaxy conditions, confirming thick disk birth? Or anomalies persist, hinting at mechanisms beyond current physics, like electrical charging from interstellar fields persisting into our system. In closing this chapter of Revelations, the initial images and chemistry stand as gateways, inviting deeper dives into a visitor that reshapes our cosmic narrative, one spectral line at a time. I'd love to know, where in the world are you tuning in from right now? And what's the time on your clock? 3 months into the chase, with the world's sharpest instruments piercing the void, 3I Atlas leaves us grasping at shadows, its core secrets eluding even our most refined probes. The nucleus diameter hovers in ambiguity, Hubble's gaze narrowing it between 320 meters and 5.6 kilometers a span from a grand stadium to a modest town. Yet this range stems not from faulty tools, but from the object's own luminous shroud, a self-generated haze that blurs direct sight. It could be a compact, brilliant orb, or a stretched, dim relic tumbling silently. Without piercing that veil, our estimates dance on the edge of guesswork, each possibility weaving a different tale of survival through galactic wanderings. This uncertainty isn't a setback, but a lure, pulling us deeper into questions about how such a small heart powers phenomena that dwarf planets. Rotation adds another veil of intrigue. Most small bodies spinning on hourly cycles, their shifting profiles creating brightness flickers we can clock like a heartbeat. Yet, 3I Atlas holds steady, its light unchanging. No rhythmic pulses to betray a turn. Is it locked in a languid spin, days long, or aligned pole-on to our view, hiding its motion? Or perhaps its surface bears uniform scars, radiation-blasted smoothness erasing contrasts. Each scenario branches into origins. Slow rotation might speak of ancient talks from a parent system's chaos, while uniformity hints at eons of cosmic weathering, particles sanding away features until only a blank slate remains. Real asteroids like Bennu, studied by OSIRIS-REx in 2018, showed chaotic tumbles from outgassing jets, acting like tiny thrusters. If 3I Atlas mirrors that but on a grander scale, its stability could mean balanced vents or a denser core resisting change, a puzzle that teases at structural secrets buried within. Water's presence twists the narrative further, evolving from hint to drama. Swift's ultraviolet scans early on caught hydroxyl radicals, those telltale fragments of water molecules shattered by solar rays, suggesting robust vapor release fitting our comet archetype. But SphereX's broader maps painted a quieter picture. Water signals dipping below thresholds, capping abundance at levels that clash with Swift's glow. Is the water there, concealed by viewing quirks or chemical masks? Or does our grasp of hydroxyl birth in cometary realms need reshaping? Laboratory simulations on Earth mimic these processes, bombarding ice analogues with UV to watch bonds break and reform. Applying those to 3I Atlas, perhaps solar wind strips hydroxyl faster than expected, or the comet's unique chemistry favors other pathways, leaving water's signature faint amid the carbon dioxide roar. This discrepancy isn't error, but invitation, urging us to refine models that once seemed solid, revealing how interstellar sojourns might alter volatile dances in ways our local samples never show. Tail morphology layers on the subtlety. Gemini South's late August capture finally affirming the anti-solar stream theory demanded. Dust pushed sunward by radiation's gentle shove. But why the delay in clarity? The tail's muted form contrasts Borisov's bold plume in 2019, suggesting grains heftier than typical, resisting the photonic breeze, or our line of sight compressing the structure into near invisibility. Dust aggregate studies from lab experiments show carbon dioxide sublimation birthing larger clusters than water's finer spray, potentially explaining the tail's restraint, a clue to composition that ties back to formation zones where volatiles froze in bulkier forms. If viewing geometry plays the trickster, as three-dimensional simulations suggest, the apparent sunward flow in Hubble's coma might be illusion, gas jets curving in complex arcs projected flat on our skyplane. A reminder that space's depths mock our two-dimensional perceptions. Activity patterns intrigue most profoundly. The sun-facing coma stretch initially baffling observers, expecting material to flee the star, not approach it. Yet optics deceive. What seems counterflow could be perspective on spiraling vents, gas erupting in fountains that loop under gravity and pressure. Or perhaps genuine oddities lurk electrical charging from solar interactions, drawing particles inward, a phenomenon glimpsed in solar system comets during strong flares, but amplified here by interstellar heritage. Beyond majors like carbon dioxide and water, trace elements beckon, organics that might fluoresce under UV, sulfur compounds hinting at volcanic analogues in parent disks, noble gases preserving isotopic ratios from stellar nucleosynthesis. Detecting these demands the fading window before conjunction blacks out the show, a race where each spectrum could unlock formation, temperatures, radiation scars, or the chemical cradle of an alien nursery. Perihelion's blackout compounds every challenge, the climax of heating and activity unfolding unseen, leaving us to piece the aftermath like detectives arriving post-heist. We'll witness only echoes, perhaps enhanced water if heat breached barriers, or persistent carbon dioxide if composition runs deeper. Ground telescopes strain at tracking speeds, pushing mechanical limits. Space assets juggle schedules as the target zips across fields. Distance devours signal, each delay weakening spectra. Yet kinematics offer solace, hyperbolic certainty, trajectory perturbations minimal, origin in the thick disk, a best bet among stars half the universe's age. This ancient lineage implies material from metal-scarce epochs, where planetary disks favored carbon over oxygen, explaining the imbalance that defies our norms. Defining interstellar essence requires orbital poetry, eccentricity approximating 1.7 seals, it unbound, a hyperbolic arc opening to infinity rather than elliptical loops. V infinity, that velocity at infinite remove from solar grasp, clocks 25 kilometers per second. Earth orbits at 30, so this carries nearly planetary momentum from elsewhere. Not zero like natives, bound to return. This is escape velocity incarnate, kinetic proof of alien birth. Detection's rarity underscores the feat. Atlas scans millions of degrees, cataloguing hundreds of thousands, yet yields one interstellar gem in a decade. Theoretical cubic light-years teem with thousands such rocks, ejected from forming systems' chaos. But faint, fast, brief, they demand wide-field revolutions like pan-stars, snaring Oumuamua or Catalina, claiming Borisov. Naming conventions etch verification. I for interstellar, earned post-vetting. 1I, 2I, 3I, each a vetted envoy from galactic debris. Implications profound. Time capsules preserving isotopes from unreachable systems, perhaps hundreds of light years distant, billions younger than our Sunday. Hyperbolics mean one-shot studies. Data from this pass the sole legacy, unlike periodic comets recycling for scrutiny. 3 visitors, 3 personas. Oumuamua's stoic cigar, accelerating sans coma, theories from hydrogen outgas to radiation sails. Borisov's classic flare, carbon monoxide rich from cold fringes. 3. I Atlas's middle enigma, carbon dioxide lead, compact coma, muted tail, splitting differences in ways that suggest sampled extremes, morphologies from needle to sphere, sizes from half kilometer to potential kilometers. Brightness and discovery vary too. Oumuamua outbound accident, Borisov inbound prep. 3I Atlas sweet spot balance. Chemistries diverge, dry processing, cold monoxide freeze, intermediate dioxide condense, hinting galactic diversity where our models falter. Cultural echoes resonate. Ancient skies saw comets as harbingers, Mesopotamian omens, or Chinese guests. Today, 3I Atlas stirs similar awe, linking human emotion to cosmic uncertainty, a bridge from myth to math where fear yields to fascination. This emotional tie fuels ʻOumuamua. Does its path's convenience whisper intent, or pure chance in infinite roles? As uncertainties mount, kinematics tracing to thick disk, but perturbations erasing specifics, the tension builds. Enough known for extraordinariness, not for explanation. December's return offers resolution, or confirmation that some secrets endure. If these unfolding layers have sparked a gentle curiosity in you, perhaps consider subscribing and turning on notifications. It's a quiet way to let more cosmic tales find you when the night calls. The universe has a knack for concealing its deepest truths in the faintest deviations. Those subtle shifts that turn predictable paths into riddles demanding our full attention. With 3i Atlas, the dynamics emerge as a quiet rebellion against our gravitational certainties, its motion adhering to Newton's laws on the surface, yet harboring undercurrents that challenge how we envision interstellar matter behaving under a foreign star's influence. Unlike 1i Oumuamua's enigmatic acceleration in 2017, a persistent nudge equaling 100,000th of Earth's gravity, defying explanation without visible gas or dust. 3i Atlas glides without such anomalies so far, its hyperbolic arc matching pure predictions within our observational margins. But this apparent obedience might mask deeper forces. The effects could surface only post-perihelion, as the object recedes and subtler influences like radiation pressure or outgassing torques reveal themselves over extended baselines. Consider the extended carbon dioxide coma, a phenomenon that stretches our understanding of scale and sustenance. A nucleus mere kilometers across, maintaining an emission region hundreds of thousands of kilometers wide, defies straightforward models. It's as if a pebble were orchestrating a cloud the size of multiple Earth orbits. Traditional sublimation, where solar heat turns ice directly to gas, falls short. The energy budget doesn't align unless the surface erupts with efficiency 100-fold beyond our solar system's comets. One emerging idea points to fragmentation. Perhaps the object isn't a monolithic core, but a loosely bound swarm of carbon dioxide-laden shards, each venting independently as they drift apart under thermal stress. Observations from Hubble show no multiple brightness peaks that would betray such a breakup. Yet the stable luminosity, despite high activity, supports this, as distributed sources could mimic a single entity's glow. If true, 3i Atlas becomes a living archive of disruption. Its pieces relics from a violent ejection in its home system, perhaps scattered by a giant planet's gravitational whip. Solar-wind interactions add another thread to this tapestry, where ultraviolet rays ionize escaping molecules, creating charged particles that entwine with the sun's magnetic field. These electromagnetic dances could propel the gas to velocities far beyond thermal escape, inflating the coma into its observed enormity, a process glimpsed in our own comets during coronal mass ejections, but amplified here by the visitor's unique composition. Real data from the Swift Observatory's detections of hydroxyl suggest photochemical reactions at play, where water traces break apart only to reform in ways that mute their signal, perhaps catalyzed by the carbon dioxide abundance. This interplay hints at a self-sustaining cycle, the coma acting as a buffer that shields the nucleus while feeding back energy through plasma waves, a feedback loop that could explain the coma's persistence even at distances where heating wanes. Rotation remains a silent player in this dynamic puzzle, its absence of detectable variation suggesting either a glacial pace or a fortuitous alignment that conceals the spin. Most small bodies bear the scars of outgassing torques, jets, firing like erratic engines, gradually altering axis and rate over time. If 3i Atlas vents as vigorously as its coma implies, those torques should imprint brightness modulations. Yet photometry reveals none. A steadiness that intrigues. Perhaps it's viewed pole-on, the rotation axis pointing straight at us, rendering cross-sectional changes invisible, or the surface uniformity, forged by interstellar particle bombardment, erases photometric clues. Drawing from asteroid studies like Psyche's metallic enigma or Bennu's boulder-strewn face, this could indicate a denser interior resisting torque, maybe a core of compacted ices from high-pressure formation, or a magnetic field remnant influencing jet directions. A speculative leap, but one grounded in observations of magnetized comets like Halley, where fields guide plasma tails. The transiting exoplanet survey satellites hints at activity beyond Jupiter's orbit. Farther than typical water sublimation thresholds tilt the story toward hypervolatiles, substances like methane or carbon monoxide that awaken at fainter solar cues. If confirmed, this early stirring implies a composition primed for response, perhaps layered from its birth disk where supervolatiles condensed first, outer shells boiling away to expose deeper reserves. This stratified model echoes real comets like Churyumov-Gerasimenko, explored by Rosetta in 2014, where onion-like layers revealed evolving outgassing as the Sun neared. For 3I Atlas, such layering could drive phased activity. Carbon monoxide traces fueling initial bursts, giving way to dioxide dominance as heat penetrates, a sequence testable in post-conjunction data when the comet emerges altered by its solar trial. Global observation campaigns orchestrate this pursuit like a symphony across continents and orbits. NASA's Science Directorate weaving a multi-mission web that harnesses every asset. Hubble delivers morphological maps, tracking coma changes with pixel precision. James Webb peels spectral layers, sniffing trace gases at parts per million sensitivity. Swift monitors ultraviolet breakdowns, charting photochemical evolution. SphereX, originally a cosmological mapper, emerges as an unlikely star, its wide-field infrared tracing the carbon dioxide sprawl and revealing absorption bands that fingerprint solid ices beneath. This synergy, Webb's pinpoint chemistry complementing SphereX's broad canvas, creates holistic views no single scope could achieve, a collaborative triumph where data streams merge to illuminate the invisible. Ground networks amplify the effort through the International Astronomical Union's rapid response grids. Gemini North's initial coma capture in Hawaii pairs with its southern twin's tail confirmation in Chile, their twin mirrors bridging hemispheres for continuous coverage. Palomar's next-generation survey adds ongoing photometry, refining orbits with each snapshot, while amateur networks fill gaps, their backyard scopes measuring brightness dips that pros might miss during scheduling conflicts. Radio arrays worldwide listen for electromagnetic whispers, perhaps electrical discharges from charged interactions, or solar wind echoes that betray hidden dynamics. Solar conjunction looms as the great interrupter, blanketing 3I Atlas in glare just as activity peaks. A 2-month void from late September to early November that tests astronomical resilience. This isn't mere inconvenience. It's a blackout during the narrative's heart, when nucleus temperatures soar and volatiles erupt most fiercely. Yet creativity counters. Mars assets like the Reconnaissance Orbiter's high-resolution imager aim for the 3rd of October close pass, 29 million kilometers distant, potentially resolving coma details from a side angle that unmasks directional flows or jet structures invisible from Earth. Spacecraft en route add opportunistic eyes. Psyche nearing 0.3 astronomical units on the 4th of September 2025. JUICE bound for Jupiter's moons glancing on the 4th of November, even OSIRIS Apex, considering late 2025 imaging. Though geometries challenge, these serendipitous alignments underscore humanity's adaptability, turning what could be loss into gain. Much like how Voyager's 1977 launches pivoted from Jupiter aims to grand tours after trajectory tweaks. For 3I Atlas, such views might capture fragmentation in action, or coma asymmetries, revealing spin, data bridging the blackout to paint a fuller portrait. International logistics mirror military precision, time allocations granted emergently, disrupting planned programs for this cosmic priority. Data sharing pacts ensure spectra from one site correlate instantly with another's images, multiplying insights a model for future transients. The European Space Agency's Planetary Defense Office extends tracking beyond science, honing techniques for hazardous asteroids. Though 3i Atlas poses none, its lessons transferable to threats that do. As conjunction nears, monitoring intensifies, telescope hours compressed into weeks, analyses rushed from months to days, a declaration of cosmic urgency, not from danger, but from ephemerality. Post-reappearance in December tests endurance. The object fainter in Virgo's dawn, racing away through Leo's bounds, signal fading in solar wind's varying embrace. Will chemistry evolve? Water asserting if barriers broke, or anomalies endure, demanding paradigm shifts? Future tools like artificial intelligence weave into this, algorithms sifting petabytes from Rubin Observatory's floods, spotting patterns in coma fluctuations, or spectral noise that human eyes overlook. AI-driven models simulate dynamics, predicting torque effects or wind interactions, evolving from current crude approximations to predictive powerhouses as data feeds train them. This tech horizon promises transformation. Machine learning correlating global feeds in real time, flagging anomalies like sudden brightness spikes or emission line shifts, accelerating discoveries in ways that echo how deep learning revolutionized exoplanet hunts via Kepler data in the 2010s. Planetary radar bounces signals off the nucleus, echoing delays to gauge size and spin, while radioscopes hunt for charged particle emissions, hinting at wind dances. Even non-traditional assets join, networks mobilizing amateurs for photometric fills, their collective eyes extending professional reach. This global watch, a tapestry of human ingenuity against cosmic transients, captures not just data, but essence, a visitor's brief whisper, teaching us to listen across borders and disciplines. If this global symphony of observation resonates with you, why not hit subscribe and ring the bell? That way, you'll catch every new episode as it drops, joining our community in exploring these wonders together. The romantic allure of pursuing an interstellar wanderer like 3i Atlas crashes against the harsh arithmetic of spaceflight, where velocities and energies demand feats beyond our current grasp. Imagine marshalling a spacecraft to rendezvous with this cosmic bullet, hurtling at over 200,000 kilometers per hour, the delta V. That critical change in velocity needed for intercept soars into realms 10 times what our mightiest rockets can muster. Chemical propulsion falls short. Even nuclear options strain against the timeline, with travel stretching years while the comet already flees back to the stars. Yet, this impossibility ignites bold visions. Engineers poring over trajectories, proposing repurposed probes like NASA's Psyche, en route to its metallic asteroid target, passing within 0.3 astronomical units on the 4th of September 2025. Psyche's cameras and spectrometers, designed for close-quarters science, could pivot for a snapshot, capturing coma details or spectral hints during the flyby, turning a routine mission into a serendipitous brush with the unknown. The European Space Agency's JUICE spacecraft, bound for Jupiter's icy moons, offers another window on the 4th of November 2025, its advanced suite potentially snagging long-range data amid Earth's observational blackout. These aren't dedicated chases but opportunistic glances, leveraging assets already in motion to snatch what we can from a visitor too swift for bespoke launches. Most audacious is the Juno redirect, orbiting Jupiter since 2016. This probe could execute a gravitational slingshot burn deep in the gas giant's well, borrowing orbital energy to hurl toward 3i Atlas for a March 2026 encounter. Calculations from Harvard's Smithsonian Center for Astrophysics detail the burn's precise timing to the hour, delta V calibrated against fuel reserves, transforming Juno from atmospheric detective to interstellar envoy. Success would yield close-ups of the nucleus, magnetic readings, or particle samples, humanity's first intimate touch with matter from another star system, a leap echoing Voyager's pivots in the 1970s. But practicality tempers the dream. Juno's mission ends in 2025, requiring approvals, fuel audits, and oversight that could derail the plan. OSIRIS-APEX, fresh from Bennu samples in 2023, EYE's late 2025 imaging, its asteroid-honed tools probing surface properties from afar. These concepts highlight our limitations. Interstellar speeds render chases science fiction with today's tech, yet they blueprint tomorrow. Solar sails harnessing photonic winds, fusion drives slashing delta-V costs, or gravitational assists chaining planets for velocity boosts. Theoretical papers since ʻOumuamua's 2017 pass explore these. From multi-planet slingshots to pre-positioned interceptors, establishing thresholds where missions shift from impossible to feasible, shifting from pursuit to origins. Natural explanations for 3I Atlas's carbon dioxide dominance. Ground the enigma in physics we know. Each pathway, a window into alien births. The snowline hypothesis stands elegant. In protoplanetary disks, volatiles freeze at distances dictated by stellar heat, water outward. Carbon dioxide in warmer middles, forming inside water's line but outside carbon dioxides, would yield a body rich in the latter, poor in the former. Akin to our asteroid belt, where temperatures vaporized water but condensed carbon volatiles. This places 3I Atlas's cradle in a zone too balmy for icy oceans, but chill enough for dioxide snow, a cosmic niche common yet unsampled until now, suggesting disks around varied stars harbor such sweet spots. Stellar diversity amplifies this. Low-mass stars, dimmer than our sun, push snow lines inward, expanding carbon dioxide realms. Luminous ones create steeper gradients, favoring dioxide through gas phase reactions. Radiation sculpting during the interstellar trek offers another lens. Cosmic rays, relentless over millions of years, break bonds selectively, perhaps dismantling water while sparing dioxide, or converting organics into it via radiolysis lab. Experiments on ice mimics show this. High-energy particles forging new compounds in frozen matrices. The reddish spectral tint from Spherex aligns, evidence of processing that darkened surfaces while preserving volatiles below. A survival story etched in chemistry. An insulating crust theory addresses the water paradox. Organics mantling the exterior, formed by radiation's alchemy, suppress sublimation. Unevenly water trapped deeper, while dioxide slips through fissures. This explains Webb's gas dominance against Spherex's solid ice hints. The crust a barrier heat must breach, a prediction testable post-perihelion when temperatures peak. Fragment hypotheses twist further. Not a solid hard, but icy aggregates, chunks separating under solar stress, each outgassing to inflate the coma. This distributed model fits the enormous envelope. Stable brightness, masking multiplicity. Subtle tail from large-grain dust. Lab studies of dioxide ice show aggregate formation differing from water's, yielding resistant particles that explain morphology. A flying swarm, born from disk collisions or ejection violence. Temperature's role weaves in subtly. At 2.5 to 3.5 astronomical units, water sublimes sluggishly while dioxide thrives. Thermodynamics naturally skewing ratios without exotic births. As perihelion warms, water should surge, evolving chemistry in ways lab rates predict a forecast for December's spectra, where persistence might signal genuine scarcity or novel mechanisms. Grain effects in coma and tail add nuance. Subtle antisolar suggests hefty particles defying pressure. Dioxide sublimation birthing aggregates. Unlike water's finds, a detail tying to origins where volatiles froze in bulk. These pathways, testable and rooted in observed physics, expand our grasp of planetary births beyond our system's snowlines, shaping compositions, radiation as evolutionary force, crusts as selective gates. Yet abundance breeds its own riddle. With myriad explanations, which combination fits this wanderer, or do they blend in unforeseen ways? Each probe's stellar disk's thermal dances, where mass and luminosity dictate chemistry, revealing a galaxy of varied recipes. Speculative edges from Avilobe balance this. If natural outgassing strains against the coma's scale, perhaps internal energies, radioactive decay, or electromagnetic relics augmented, or trajectories optimality, hints at navigation. Loeb's essays, prescient on the tale's August reveal, frame these as alternatives, not assertions, urging tests like high-cadence photometry for artificial glimmers or spectra for exotic lines. Mainstream counters with self-consistency. Dioxide snowlines suffice without invoking tech, yet openness to outliers echoes science's progress, from pulsars mistaken for signals to quasars redefining galaxies. Source tracing refines further. Kinematics point to thick disk, 8 to 12 billion years old, metal-poor environs favoring carbon over oxygen, ejections from giant planets or flybys launching such debris. Population studies from the trio suggest biases our surveys snag active ones, missing dry relics, while Rubin promises statistical floods, dozens yearly transforming anecdotes to trends. Isotopic hunts push limits. Ratios could fingerprint stellar mass, age, metallicity, distinguishing thick disk from thin, but faint signals demand conjunction's edge. Early media's extragalactic claims fade against Milky Way kinematics, the path constraining travel to galactic scales. Timing's coincidence, or galactic dynamics pattern, fuels ʻOumuamua. Thick disk origin means a relic from dark ages, surviving supernovae. Its arrival a bridge to ancient formations. Post-perihelion might confirm thermodynamics, or demand revisions. Each outcome a step toward grasping interstellar diversity. These threads converge on a visitor that, while explaining itself through nature, invites us to question boundaries. Where does physics end and wonder begin? I'd be delighted to hear, where are you listening from this evening? And what time is it there? While 3i Atlas captivates with its veil of interstellar enigma, gliding harmlessly at a staggering 268 million kilometers from Earth, a far more intimate cosmic drama unfolds with Apophis, our solar system's unassuming neighbor that once whispered of potential catastrophe. This 340-meter behemoth of silicate rock and nickel iron, discovered on the 19th of June 2004 by astronomers at Kitt Peak, initially bore the bland label 2004 MN4, before earning its moniker from the Egyptian god of chaos, a fitting nod to the turmoil it stirred. Apophis doesn't hail from distant stars. It's a homegrown wanderer, part of the Apollo group of near-Earth asteroids whose orbits cross our own, looping in elliptical paths that bring periodic brushes with destiny. Its story isn't one of exotic chemistry or ghostly comas, but of gravitational near misses that test humanity's vigilance, turning what could be routine into a pulse-quickening reminder of our planet's fragility. Early calculations painted a chilling picture. A 2.7% chance of collision on the 13th of April, 2029. Friday the 13th, no less, earning it a level 4 on the Torino scale, the highest for any asteroid at the time. That probability, derived from just 74 observations over 64 days, wasn't a doomsayer's exaggeration, but a stark measure of uncertainty. The orbital ellipse, wide enough to encompass Earth in its error bars, Astronomers mobilized globally, their telescopes pivoting to accumulate data that gradually shrank the shadows of doubt. By December 2004, archival images extended the arc back to March, refining the path and dialing down the odds. Yet the gravitational keyhole loomed a narrow 610-meter window during the 2029 flyby that, if threaded, could deflect Apophis onto a 2036 impact course. This keyhole concept, a quirk of celestial billiards, underscores Apophis's intrigue. Close encounters aren't endpoints but pivots, where Earth's tug could rewrite futures. Unlike 3I Atlas's one-way hyperbolic sprint, immune to such perturbations as it escapes forever, Apophis orbits in our gravitational web, its path evolving under planetary influences, and the Yarkovsky effect, that subtle thermal recoil where absorbed sunlight re-radiates unevenly, nudging the asteroid like a slow-motion rocket. Detected in 2021 at -70 meters per year, this drift sealed the deal, ruling out the keyhole and confirming safety for over a century. NASA analysis echoes this. Earth is safe from asteroid Apophis for 100+ years, a verdict born from 2 decades of relentless tracking, transforming alarm into assurance. Yet, Apophis's tale weaves deeper into Earth's own history of cosmic scars, linking to events that shaped life itself. Recall Chicxulub, the 6-mile-wide crater off Mexico's Yucatan, forged 66 million years ago by a 10-kilometer asteroid that ended the dinosaurs' reign, blanketing the globe in dust that chilled climates and starved ecosystems. Or Tunguska, in 1908, a 50-meter airburst over Siberia, flattening 2,000 square kilometers of forest, its shockwave circling the Earth twice, no crater, just devastation from compressive heat and blast. These aren't ancient myths, but geological fingerprints, reminders that our blue marble bears the pox of interstellar violence. With Apophis's size capable of a 5-kilometer crater, and regional tsunamis evoking scaled-down versions that could disrupt modern civilization without global extinction, Tunguska's link to life intrigues further. Some theories posit that such impacts delivered organics, water, and even microbial seeds, kickstarting biology in primordial soups. Apophis, as an S-type asteroid rich in silicates and metals, might mirror those ancient deliverers, its composition hinting at the raw materials that built planets. Probing it reveals not just threats, but origins. How disk debris coalesced into worlds, with near-Earth asteroids as leftover fragments, their orbits chaotic from Jupiter's meddling. The Arton, Apollo, Amor, and Atira groups classify these, each with evolutionary tales. Arton's hugging inside Earth's orbit, Apollo's crossing boldly like Apophis, Amor's approaching from afar, but potentially drifting inward, Attiras tucked sunward and elusive. Over 34,000 catalogued, yet tens of thousands lurk unseen, their dark surfaces evading optical hunts until infrared eyes like Neo Surveyor launch in late 2027. Apophis's rehabilitation from menace to muse stems from this cataloguing fervor. Surveys like Atlas, not the comet's discoverer, but the asteroid terrestrial impact last alert system, scanning skies for hazards, flagging potentials for follow-up. Its 2004 scare spurred NASA's Planetary Defense Coordination Office in 2016, coordinating detections, characterizations, and mitigations. The double asteroid redirection test in 2022 slammed into Dimorphos, shortening its orbit by 32 minutes. Proving kinetic impacts work with momentum enhancement from ejected debris. Hera, launching in 2024, arrives in 2026 to survey the aftermath. Measuring crater depth and structural shifts, lessons directly applicable to deflecting Apophis like threats. But curiosity lingers on what if. An Apophis strike would unleash 500 megatons, vaporizing ground zero, igniting fires across 15 kilometers, blasting waves flattening 50 kilometers out. Oceanic hits vaporize water into steam tsunamis 10 to 20 meters high, rivaling the 2004 Indian Ocean disaster that claimed 230,000 lives. Climate dips 1 to 2 degrees for years, disrupting harvests for billions, cascading into economic shocks exceeding $1 trillion. Psychological ripples would redefine humanity's cosmic view, from passive observers to active guardians, echoing how Chicxulub's fallout paved evolution's path for mammals. This contrasts sharply with 3I Atlas's benign spectacle. No evolving orbits, no Yarkovsky nudges, just a straight shot through, its mysteries chemical rather than kinetic. While the comet's carbon dioxide cloak teases alien formations, Apophis demands practical readiness, cataloguing over 2,000 potentially hazardous asteroids, those over 140 meters with intersections under 0.05 astronomical units. Surveys accelerate. 3,000 new near-Earth asteroids yearly. 90% of kilometer giants found and cleared, but 40% or less of city killers known. Gaps Neo Surveyor and Rubin aim to fill with infrared sensitivity and rapid cadences. Apophis's 2029 pass. At 31,600 kilometers inside geostationary orbits, offers a natural lab. Tidal forces, 50 times its self-gravity, could trigger quakes, landslides, exposing fresh interiors for spectral shifts. Goldstone radar and Green Bank will map meter-scale changes, photometry tracking rotation tweaks from 30.6 hours. This data calibrates deflection models, informing if rubble piles shatter or hold under stress. Crucial for scaling DART's success to real threats. Historical parallels enrich the narrative. Chelyabinsk's 2013 airburst, a 20-meter surprise injuring 1,500, underscores detection gaps sunward approaches blind us. As with that event, scale to Apophis, and regional havoc multiplies, yet its story flipped, from doom to data, through observation's power. A blueprint for threats like 2024 PT, 5 or 2025 RX-12, mundane passers-by that warrant watch. Tomo builds. Will Apophis's flyby reveal internal coherence beyond models, or fragility demanding new deflection tactics? Its S-type makeup, 23% reflectivity, elongated form, all factors in Yarkovsky's push, detected via astrometry, precise to arcsecond fractions over years. This evolution, from 2004's alarm to 2021's drift confirmation, eliminated 2036 risks, but orbits shift eternally, demanding vigilance. Near-Earth groups' dynamics fascinate. Apollos, like Apophis, numbering thousands, cross twice per loop, maximizing encounters. Amors lurk as precursors, perturbations inching them closer. Attends and Atiras, sun-hugging, evade easy spots, their discoveries spiking with space-based eyes. Over 34,000 total. Discovery curve, climbing from 200 in 1990 to thousands yearly. Yet undiscovered tens of thousands pose cumulative risks, low per object, but stacking over millennia. Planetary Defenses Web, NASA's Office, Europe's Situational Awareness, United Nations Asteroid Warning Network coordinates this, sharing data to shrink uncertainties fast, avoiding Apophis-like scares. DART's beta factor of 3.6 ejector boosting impact hints at efficiency, but Apophis scale demands multiples, perhaps fleets for larger threats. Linking to life, impacts like Tunguska flattened forests, but may have seeded volatiles. Apophis kin delivering building blocks. Chicxulub's iridium layer marks the Cretaceous end. but sparked mammalian dawn destruction birthing opportunity. A cosmic cycle where threats forge resilience. Apophysis legacy. From chaos god to teacher, its safe pass a rehearsal for real perils. Data honing tools like Osiris Apex's 2029 arrival. Thrusters disturbing surfaces for subsurface peaks. This repurposing from Bennu sampler to Apophis watcher mirrors adaptability, probing tidal aftermath for deflection insights. In this duality, 3i Atlas's harmless mystique pales against Apophis's tangible lessons, urging us to probe not just stars, but our backyard's quiet dangers, where probability trumps spectacle. I'd love to know, where are you listening from this evening? And what time is it there? Let's delve into the shadowy what-ifs surrounding an asteroid like Apophis, where the line between cosmic curiosity and earthly peril blurs in ways that stir the imagination without overwhelming the spirit. Picture a body 340 meters wide, a rugged mass of silicate rock laced with nickel and iron, barreling toward our world at 25 kilometers per second, not as a distant speck like 3i Atlas, but on a trajectory that intersects our fragile blue sphere. The kinetic energy unleashed would rival 500 megatons of TNT, a force tenfold the might of the largest nuclear detonation in history, the Soviet Tsar bomber of 1961. This isn't abstract speculation. It's rooted in the physics of impacts we've pieced together, from craters scarring our planet and beyond, each one a frozen echo of violence that reshaped landscapes and lives. On land, the strike would carve a crater 4 to 5 kilometers across, depending on the soil's give and the angle of descent. Imagine a gaping wound in the Earth's crust, vaporizing everything within kilometers as temperatures spike to solar surface levels in a flash. The fireball, expanding to 15 kilometers wide, would ignite widespread infernos, charring forests and cities alike, while thermal radiation sears life from the zone in an instant. Beyond that, the blast wave surges outward at supersonic speeds, toppling structures and claiming lives up to 50 kilometers away, a ripple of destruction that doesn't discriminate between bustling metropolises or quiet countrysides. Seismic tremors would radiate globally, triggering quakes detectable on the far side of the world, potentially destabilizing fault lines and compounding chaos with aftershocks that linger for days. Shift the scenario to an ocean impact, and the dynamics evolve into something even more insidious. Water, far from cushioning the blow, behaves like a rigid barrier at such velocities, the asteroid punching through to vaporize millions of tons into superheated steam. This explosive release births tsunamis towering 10 to 20 meters high, racing across basins at jetliner speeds, slamming into coastlines with little warning. The 2004 Indian Ocean tsunami, spawned by a magnitude 9.1 quake, claimed over 230,000 lives across 14 nations. Waves from an Apophis-scale event could dwarf that, inundating ports, erasing islands, and flooding inland for kilometers, salting farmlands and displacing millions. Coastal geography plays a role. A hit in the shallow Gulf of Mexico might amplify waves through funneling effects, while a deep Pacific strike disperses energy but still threatens distant shores like Hawaii or California. Climate repercussions weave a longer thread of consequence, injecting dust and aerosols into the stratosphere where they linger for months or years, dimming sunlight and cooling global temperatures by 1 to 2 degrees Celsius. This isn't the full nuclear winter of larger impacts, like the 6-kilometer Chicxulub asteroid that chilled the planet for decades 66 million years ago, starving dinosaurs into extinction and paving the way for mammalian rise. But even this subtler shift disrupts agriculture, shortened growing seasons, failed harvests, and food shortages for billions, echoing the 1816 year without a summer from Mount Tambora's eruption, when frosts killed crops mid-year and famine stalked Europe. Modern supply chains, already fragile, would fracture imagine empty shelves in supermarkets worldwide, economic ripples cascading into recessions deeper than the 2008 financial crisis, with costs soaring beyond $1 trillion in direct damage alone. Social fabrics would fray under such strain, psychological scars running as deep as physical ones. Unlike earthquakes or hurricanes, confined to regions with recovery paths, an asteroid impact carries a universal dread. The knowledge that our home remains a target in the cosmic shooting gallery is vulnerable to random bolts from the blue. Historical echoes abound. The 1908 Tunguska event, a 50-meter airburst over Siberia, flattened 2,000 square kilometers of taiga without a crater, its shockwaves circling the globe twice and felling 80 million trees. No deaths due to remoteness, but scale it to Apophis over a city like New York or Tokyo, and casualties climb into millions, with survivors grappling with trauma that reshapes societies, perhaps spurring migrations, policy overhauls, or even philosophical shifts towards space as a frontier to tame rather than fear. The 2013 Chelyabinsk meteor, a mere 20-meter surprise bursting over Russia, injured 1,500 with its shockwave shattering windows across a vast area, causing millions in damage without ground contact. Multiply that by Apophis's volume 60 times greater, and the narrative turns nightmarish. Airbursts at altitude could blanket regions in firestorms, while ground strikes eject molten debris raining down like apocalyptic hail. Yet these horrors aren't inevitable. They're contingencies that highlight why planetary defense has matured, from fringe concern to strategic imperative, blending technology with foresight to avert what nature might otherwise deliver. Enter the realm of potentially hazardous asteroids, or PHAs, those over 140 meters wide with orbits intersecting Earth's at less than 0.05 astronomical units, about 7.5 million kilometers. This threshold isn't arbitrary. It's the size where regional devastation becomes feasible, balanced against frequency. Smaller rocks hit more often but burn up. Larger ones rarer, but globally threatening. Over 2,000 catalogued, with hundreds added yearly, yet estimates whisper tens of thousands unseen, lurking in sun glare or dark hues that evade optical scopes. Apophis fits this mold, its S-type makeup, silicates and metals, reflecting 23% of light, making it a prototype for threats that blend into the night, until surveys like the Asteroid Terrestrial Impact Last Alert System flag them. Defense strategies pivot on this knowledge, with NASA's Double Asteroid Redirection Test in 2022 marking a milestone. A spacecraft slamming into Dimorphos, the moonlet of Didymos, at high speed, shortening its orbit by 32 minutes, triple the 10-minute benchmark for success. The momentum boost, or beta factor of 3.6, came from ejected debris acting like extra thrust, validating models that predicted such amplification for rubble pile structures. This wasn't random. Dimorphos, a loose aggregate like many asteroids, responded as theorized, offering blueprints for nudging larger threats off course with years of lead time. The European Space Agency's Hera, launched in October 2024, arrives in late 2026 to scrutinize the aftermath crater dimensions, surface alterations, internal shifts from the impact. Hera's suite will map gravitational changes, perhaps revealing how the collision redistributed mass or triggered mini-quakes, insights crucial for scaling to Apophis-sized bodies. This tag team, DART as the kinetic punch, Hera as the forensic eye, establishes a paradigm for mitigation: strike to deflect, follow to learn, refining tactics for diverse asteroid types, from metallic psyches to carbonaceous chondrites rich in volatiles. Humanity's angle infuses deeper meaning. These efforts forge unity, transcending borders as agencies like NASA's Planetary Defense Coordination Office collaborate with Europe's Space Situational Awareness and the United Nations International Asteroid Warning Network. Apophyse's scare in 2004 spurred this congressional hearings, funding surges, diplomatic ties, ensuring data flows freely, turning potential panic into coordinated calm. It's a testament to collective will. Astronomers in Chile spotting threats, engineers in California designing deflectors, policymakers in Geneva crafting protocols, a global web where one nation's telescope aids another's safety. Turmoil arises in future defenses. What if warnings shorten to months? Rapid response concepts emerge, prepositioned impactors at Lagrange points, ready to launch like sentinels, or gravity tractors, spacecraft hovering to tug via mutual pull over years. Nuclear options linger in studies, not as explosions but standoff bursts vaporizing surfaces for thrust, though ethics demand caution. Apophyse's safe pass tests these indirectly. Tidal observations could reveal cohesion, informing if impacts shatter or redirect intact. Historical defenses echo too. Ancient cultures tracked comets as portents, building observatories like Stonehenge for celestial vigilance. Today, we evolve that with Rubin Observatory's 2025 debut, scanning skies for PHAs at rates dwarfing predecessors. Neo-Surveyor, infrared hunter in 2027, targets dark lurkers, closing gaps where Chelyabinsk slipped through. Economic stakes heighten intrigue. A $1 trillion hit dwarfs Katrina's $125 billion in 2005 or Tohoku's $200 billion in 2011, yet prevention costs fractions. DART, at $325 million, proves investment yields. Socially, unity blooms. Impacts don't respect nations, fostering alliances like climate pacts, where shared vulnerability breeds cooperation. In this mosaic, Apophyse's narrative from chaos to control stirs wonder. How might deflection spark technological boons, like advanced propulsion spilling into exploration, or inspire art, films reimagining impacts not as ends but turning points? Humanity rising, resilient? These layers reveal defense as evolution's next step, turning cosmic roulette into calculated strategy, where turmoil drives not fear, but innovation. The 13th of April 2029 dawns as a date etched in astronomical lore, when Apophis slices through our skies at a mere 31,600 kilometers above Earth's surface, a whisper away, in cosmic terms, threading between our world and the geostationary satellites that beam signals across continents. This isn't the remote grace of 3i Atlas fading into interstellar obscurity. It's an intimate rendezvous with a 340-meter giant, visible to the naked eye from swaths of Europe, Africa, and Western Asia, appearing as a swift-moving star against the twilight canvas. Weather willing, observers might trace its arc without aids, a fleeting streak that transforms abstract orbital data into a tangible thrill, stirring that primal sense of wonder at something vast and ancient, brushing our atmospheric fringe. What makes this pass mesmerizing isn't just proximity closer than any comparable asteroid in recorded annals, but the gravitational tango it dances with Earth, a force 50 times the rock's own self-gravity stretching and squeezing its form like cosmic taffy. Tidal stresses peak at 21 hours 46 minutes, universal time, potentially triggering internal quakes or surface slippages, where loose regolith cascades in slow-motion avalanches, exposing buried layers, untouched for eons. Scientists speculate, will boulders redistribute, carving new shadows on its elongated silhouette? Or might the body subtly reshape, its rubble pile nature loose, aggregates held by feeble bonds yielding clues to how such worlds endure solar systems churn? This natural stress test, unobserved before at this scale, promises revelations about asteroid resilience, perhaps unveiling fractures that hint at formation violence billions of years back when planetary disks hurled debris into chaotic orbits. Radar eyes will capture the minutiae, with Goldstone Solar System radar in California and Green Banks Telescope in West Virginia achieving meter-level precision, mapping every contour shift or boulder tumble. These facilities, honed on past visitors like Bennu, will compare pre-flyby models' Apophyse's potato-like form, rotating every 30.6 hours to post-encounter reality, detecting if tides accelerated or slowed the spin, or tilted its axis in ways that alter future paths. Imagine the data streaming in, echoes bouncing off surfaces, revealing fresh exposures with different radar reflectivity, perhaps brighter metals glinting from depths, or darker organics unearthed by the pull. This isn't passive watching, it's active interrogation. Waves probing the invisible to sketch three-dimensional portraits that evolve in real time, feeding models that predict how similar bodies might fracture under deflection attempts. Optical networks join the vigil. Telescopes worldwide monitoring brightness, fluctuations that betray rotational tweaks, or dust ejections from tidal cracks. Infrared scopes like those on the Near-Earth Object Surveyor, launching no earlier than late 2027, could catch thermal anomalies, hotspots where friction from shifts radiates excess heat, or cooler patches of newly bared ice if volatiles lurk within. The Catalina Sky Survey and Lincoln Near-Earth Asteroid Research will coordinate photometry, measuring light curves to quantify spin changes, while amateur astronomers, armed with backyard setups, contribute global coverage, their data filling gaps when professional scopes pivot elsewhere. This citizen science swell, coordinated by the International Astronomical Union, turns the event into a planetary party where backyard stargazers might spot subtle color shifts reddened by space weathering, giving way to pristine hues, adding personal threads to the scientific tapestry. OSIRIS-APEX's arrival in June 2029 elevates the scrutiny. This repurposed probe, fresh from Bennu's sample return in 2023, spending 18 months orbiting Apophis, its instruments dissecting the aftermath. Cameras will resolve centimeter-scale features, hunting for landslide scars or boulder migrations triggered by the flyby. Spectrometers will sniff compositional changes, perhaps detecting volatiles released from cracked interiors. The thruster maneuver stands out, descending to 25 meters, firing engines to loft surface dust without contact, exposing subsurfaces for remote analysis. A bold probe of hidden realms, testing if tides loosened the regolith or compacted it further. Navigation challenges abound. Apophis' irregular shape creates lumpy gravity fields, and if tides altered rotation, OSIRIS-APEX must adapt on the fly, its autonomy a preview of smarter probes to come. This data bonanza feeds into broader defenses, validating simulations for kinetic impacts like DART's 2022 success on Dimorphos. If Apophis holds firm, it suggests coherent structures needing heavier hits. If it yields dramatically, lighter nudges might suffice for threats. The European Space Agency's Hera, arriving at Didymos in late 2026, parallels this. Its post-DART autopsy informing Apophis interpretations, crater morphologies, ejector patterns, cross-pollinating knowledge across missions. Tormal swells around unexpected yields, Will magnetic readings from Osiris Apex detect fields induced by tides, or particle emissions from stressed materials? Real asteroids like Psyche hint at metallic cores generating fields. And if Apophis echoes that, it could rewrite deflection strategies, where electromagnetic tugs become viable. Future missions loom tantalizingly. Prepositioned interceptors at stable points, ready for rapid redirects, or gravity tractors hovering to pull gently over months, avoiding fragmentation risks. Artificial intelligence weaves in, algorithms sifting radar returns for anomalies, predicting tidal responses in simulations that evolve with each data, burst AI as co-pilot, spotting patterns humans miss, like subtle pre-flyby wobbles hinting at internal voids. Neo Surveyor's infrared gaze, optimized for dark lurkers, promises to uncover Apophis kin by the hundreds, its space-based vantage, evading atmospheric blur to catalogue threats in the 140 to 500 meter range city killers that slip optical nets. Launching late 2027, it complements Rubin Observatory's 2025 operations, whose legacy survey scans the southern sky every 3 nights, potentially spotting 70 interstellar visitors yearly alongside near-Earth hordes. Rubin's 3.2 gigapixel camera, mapping with depth that dwarfs predecessors, will refine orbits to eliminate false alarms, turning raw detections into precise predictions. These tools birth a new era, statistical science over anecdotes, where population trends reveal ejection rates from distant disks or migration patterns in our system. Interstellar like 3i Atlas might surge in counts, their chemistries charting galactic diversity, carbon monoxide from cold edges, dioxide from middles, while near-Earth like Apophis inform hazard maps, prioritizing watches on Apollos with crossing potentials. AI's role expands. Machine learning training on Apophis data to forecast Yarkovsky drifts for unseen objects, or simulating deflections with virtual twins, tweaking variables like composition or spin to optimize outcomes. Ethical horizons intrigue. Who decides deflections? United Nations frameworks like the Space Mission Planning Advisory Group draft guidelines ensuring international buy-in for missions that alter celestial bodies. Apophis's pass tests these softly satellite operators adjusting for its geostationary thread, treating it as debris drill, preparing for crowded orbits where impacts cascade into Kessler syndrome, chains of collisions littering space with shards. Cultural ripples fascinate. The 2029 visibility might inspire art, novels reimagining close calls as awakenings, or educational surges, where schools simulate deflections, fostering STEM passions. Historical ties. Ancient Mayans tracked Venus transits for calendars. Today, we track asteroids for survival, a evolution from prophecy to prevention. Economic angles add layers. Prevention's modest costs dart at $325 million pale against trillion-dollar hits, justifying investments that spill into tech like advanced radars for weather or AI for medicine. Tomo lingers on surprises. If Apophis ejects dust during tides, spectral analysis might reveal organics linking to life seeds or unexpected minerals hinting at rare formations. This convergence, observation, tech, ethics, paints 2029 as pivotal. Apophis, a catalyst turning vigilance into vision, where cosmic brushes yield not fear, but fortified futures under starry vaults. As the threads of 3i Atlas and Apophis intertwine in our exploration, a profound realization emerges from the shadows of space. The true peril isn't the enigmatic visitor from the stars or the lurking neighbor in our orbital backyard, but the subtle creep of complacency that dulls our cosmic vigilance. 3i Atlas, with its hyperbolic sprint and chemical quirks, dances on the edge of wonder, a fleeting messenger whose carbon dioxide shroud and extended coma tease at galactic diversity, yet poses no shadow over our world. It whispers of ancient stellar nurseries, where snow lines drew boundaries between volatiles, forging bodies that wander eons before awakening in our sun's glow. Apophis, by contrast, embodies the familiar yet formidable. Its elliptical loop a reminder that our solar system harbors quiet sentinels whose paths could one day align with catastrophe. Together, they form a duality that beckons us to peer deeper, not just into the void, but into our own readiness to confront what lies hidden in plain sight. Complacency, that insidious drift toward assuming safety in the known, arises when spectacles like 3i Atlas eclipse the steady threats of near-Earth asteroids. We've catalogued over 34,000 such wanderers, their orbits weaving through our neighborhood in patterns governed by gravity's unyielding hand, yet tens of thousands more evade our gaze. Dark silhouettes against the sun's glare or faint echoes in the infrared. What if one of these unseen kin, perhaps a sibling to Apophis in size and composition, slips through our surveys undetected until too late? The Yarkovsky effect, that thermal whisper nudging paths over millennia, could subtly steer it from harmless arc to fateful intersection, a slow burn of probability building toward impact. It's this gradual evolution, not the dramatic blaze of an interstellar comet, that keeps the cosmic game intriguing. Orbits aren't static. They're living equations, perturbed by Jupiter's massive pull or Venus's closer tugs, reshaping futures in ways that demand constant recalibration. ʻOumuamua lingers in the gaps of our knowledge. How many Apophis-like bodies orbit in the Aten group, hugging sunward and eluding detection during twilight windows? Or in the Amor ranks, approaching from afar but potentially migrating inward under resonant forces. Like cosmic nomads drawn to our warmth, the Apollo crossers, numbering in the thousands, maximize encounters with their dual intersections per loop. Each pass a roll of gravitational dice. Apophis itself, once a 2.7% harbinger on Friday the 13th, 2029, now cleared by precise astrometry and drift measurements, serves as a case study in transformation. But what of the next? NEO Surveyor's launch in late 2027 promises to illuminate these shadows, its infrared vision piercing reflectivity biases to uncover the city killers in the 140 to 500 meter realm, objects capable of regional havoc without global doom. Imagine the discoveries. A swarm of dark, carbonaceous types, rich in organics that could trace back to life's seeds, or metallic psyches hinting at shattered planetary cores, each adding layers to the puzzle of our system's formative chaos. This ʻOumuamua extends to Deflection's frontiers, where DART's 2022 triumph on Dimorphos, shortening an orbit by 32 minutes through kinetic, might opens doors to scenarios where we actively rewrite asteroid fates. The beta factor's 3.6 amplification from ejector suggests rubble piles multiply our efforts. But what if a threat proves denser, like a monolithic iron-nickel beast resisting our strikes? Hera's 2026 arrival at Didymos will dissect the crater's secrets, measuring how the impact rippled through the moonlet's structure, perhaps revealing voids or cohesions that inform scaling to larger perils. Gravity tractors hover in conceptual sketches, spacecraft lingering nearby, their mutual pull gently towing over years while nuclear standoff bursts vaporize surfaces for thrust, ethical quandaries swirling around their use. Each method teases possibilities. Could we one day preposition fleets at Lagrange points, ready to swarm a detected hazard, or harness solar sails for photonic nudges that accumulate over decades? Apophis's 2029 flyby amplifies this intrigue. its tidal encounter a live experiment in asteroid anatomy. At 31,600 kilometers, Earth's grasp will exert forces that might trigger microquakes, redistributing boulders or exposing subsurface veins. Will we detect magnetic anomalies from induced fields, or volatile releases from cracked ices? OSIRIS-APEX's June arrival, repurposed from Bennu's treasures, will orbit for 18 months, its thrusters disturbing regolith to unveil hidden compositions, perhaps organics preserved since the solar nebula's swirl. This data could unravel how tides mimic deflection stresses, testing if loose aggregates shatter or rebound. A preview for missions targeting similar threats. ʻOumuamua builds. What if the flyby ejects a mini-swarm of particles, analyzable for isotopic clues to Apophis's birth, linking it to ancient collisions that littered the inner system? Beyond mechanics, the human element weaves a compelling layer. International webs like the United Nations Asteroid Warning Network, sharing alerts across borders, echo how shared skies foster unity. Apophis's scare spurred this, from 2004's congressional probes to today's coordinated vigils, where Chilean telescopes spot, Californian radars map, and Geneva policies guide. What alliances might form if a true threat emerges? Nations pooling resources for a deflection armada, turning rivalry into resilience. Ethical horizons tantalize. Who authorizes a nudge that alters a celestial body, potentially affecting future generations' skies, or if it harbors scientific treasures like preserved volatiles? Rubin Observatory's 2025 Legacy Survey adds fuel. Its rapid scans potentially unearthing 70 interstellar kin yearly, alongside near-Earth hordes, blending 3I Atlas's mystique with Apophis's pragmatism. Will we find hybrids interstellar rocks captured into solar orbits, their chemistries merging galactic recipes with local evolutions? ʻOumuamua in populations. Statistical trends might reveal ejection hotspots from young star clusters, or migration waves from the Oort cloud, painting a dynamic galaxy where debris flows like rivers between systems. Complacency's shadow looms here, that quiet erosion, where successes like Apophis's clearance breed overconfidence, funding waning as threats seem tamed, yet probability whispers otherwise. Low per asteroid, but cumulative over centuries, an inevitable intersection unless vigilance endures. This duality, exotic harmlessness versus familiar risk, mirrors broader enigmas. Climate's slow boil, pandemic's stealthy spread, where ʻOumuamua drives preparation, turning unknowns into navigable paths. OSIRIS-APEX's thruster test intrigues further. Lofting dust without touch, it might expose layers forged in protoplanetary fires, isotopes dating to the sun's ignition, or organics, hinting at panspermia's reach. If tides from the flyby loosen bonds, the disturbance could reveal internal voids, acoustic waves from the blast mapping density, like seismic probes on Earth ʻOumuamua in echoes. What stories do those waves tell of collisions past, or pressures that compacted the core? Future visions tantalize. AI-enhanced surveys predicting paths from partial arcs, or quantum sensors detecting gravitational whispers from distant threats. Apophis as catalyst. Its data refining Yarkovsky models, perhaps uncovering spin-orbit resonances that stabilize or destabilize populations, a key to forecasting long-term risks. In this cosmic chess, where moves span eons, ʻOumuamua sustains us. 3I Atlas as the wild card, Apophis the steady player, together urging questions that bind humanity to the stars. What unseen guardians watch our skies, and how might we join them? If these cosmic reflections have you pondering the stars a bit longer tonight, consider subscribing and hitting the bell. It's a simple way to catch more mysteries as they unfold And maybe share your thoughts in the comments on what intrigues you most about these wanderers.